So welcome everybody. I'd like to begin by acknowledging the traditional custodians of the land on which we meet today. And despite the fact that we are meeting virtually, each and every one of us is on traditional Aboriginal lands. And I'd like to pay my respects to elders past, present and emerging, and extend that respect to any Aboriginal elders who are joining us this evening. Welcome. Welcome to an unusual event. Some of you will know that we have been running a series of masterclasses leading up to the New South Wales Smart Places Summit, originally planned for June 22nd, and now very likely to land on August the 6th. Not surprisingly, we've had to delay the event because of COVID. And our ability to move from what was a hybrid in-person and online event to a fully online event took a little longer than we thought, but nonetheless, that's where we'll go. What it's meant though is we've had an opportunity to put in place two more in our masterclass series, and I'm delighted that we have Peter and Michael with us this evening to talk to us about some futuristic stuff. All the other masterclasses leading up to the original planned summit date, we're talking about issues, contemporary issues around data use, governance, AI, digital twins, around cybersecurity, precincts. And we took the opportunity with the delay to talk about some really futuristic stuff. So the last session, number 11, was on 6G, which was, I think, a lot of fun. And now we're talking about quantum computing, which I think is going to be the most fun session we're going to have. And what we know about quantum computing, of course, is that it will be a massive game changer. And it is something that will require us to rethink many of our standard ways of doing things. But we've got a little bit of time between now and when quantum computing starts to become an issue of great significance. But nonetheless, we're absolutely thrilled to have two incredible speakers with us this evening. We've got Peter Turner, who's the CEO of the Sydney Quantum Academy, and Michael Bremner, who's a professor at the University of Technology, Sydney. I forgot to introduce myself. My name is Ian Opperman. I'm the day job Chief Data Scientist for the New South Wales Government, but also a visiting or an adjunct professor at the University of Technology and the president of the Australian Computer Society. And so I'm delighted that on behalf of all of those organisations to welcome here this evening. Just a little bit of housekeeping in terms of how we run these sessions. Those of you that have joined previous ones will know that what we ask you to do is stay on mute during the beginning of the presentation, and to avoid any platform issues, we just ask you to keep your video off. Questions can be posted in the chat at any time, and after the presentations, after Peter and Michael do their presentations, what we'll do is we'll ask people to come off mute, turn on the video and ask the questions. And hopefully there's an opportunity to get a little interactive around those sessions. I have not seen the material to be presented tonight. I'm literally on the edge of my seat in anticipation, and I really cannot wait. So folks, without further ado, we will also, we'll be recording the session, so hopefully that's not a problem, and we'll provide a link to the access to the recording at the end. And we've asked the presenters if they'd be willing to make a subset of their slides available to us, which we then subsequently share. So the session will be recorded. We'll get a subset of the slides available and out to you. And without further ado, it is my enormous pleasure to welcome Peter and Michael to talk to us about quantum computing now and in the future.
Great. Thanks very much, Ian. Can everyone hear me all right?
Perfect.
Great. Yeah, thanks again, Ian. Thanks, Mark. Thanks, everyone, for having us. This is a rare opportunity for me to talk about science, which doesn't happen so much anymore in my new role at the Sydney Quantum Academy. So very exciting. I'm going to share my screen, if you bear with me for a moment. Can everyone see a presentation now? Oops.
Yes, it's there. There we go.
Is that all right?
Okay,
great. Thanks. All right. Yeah, so I'm Peter Turner, CEO of the Sydney Quantum Academy and a quantum information theorist, also honorary position at the Macquarie University in the quantum engineering group there. And yeah, my background is physics, and in particular, 15, 20 years now in the quantum information field. So going to talk to you today about quantum computing today and into the future, as we mentioned, and let me just try to move this forward. There we go. So I'm going to start off with some history of the field and a little bit of background, and then I've taken on the challenge to try to talk about some physics and get across a little bit of the wackiness of the kinds of systems that we're trying to harness here in this field, which will lead us into a discussion of the advantage of quantum information over classical information in this quantum computational supremacy term that you might have heard of. And then Michael's going to jump in and take over in a deep dive into algorithms and applications and some of the issues and things to keep in mind around that. And then I'll come back and talk a little bit about Sydney and the City Quantum Academy, if that's all right. So yeah, I feel like well, not a bad way to get into a field like this is to talk about the history a little bit. So this will be very brief and very selective. And if you want to kind of impress people, impress your friends down the road when you talk about quantum information, you might want to go back this far. 1969, which technically is not that far historically for a lot of physics concepts, but for quantum information, things are quite young. And this was Stephen Wiesner's work, which didn't get published until a decade or two later. But actually, the idea at the root of quantum cryptography goes back to this idea and conjugate coding and quantum money. So jumping ahead, I want to introduce the term quantum sensing, and there's several examples I could have chosen. I've chosen this one as a famous one, 1980, Carl Caves, Kip Thorne, and others, because gravitational wave detection, we've probably all heard of in the news in the last few years, is one of the coolest things we've done scientifically recently. And quantum sensing and in squeezed light, if you dig into those articles, you might hear those terms used, is part of that story. 1981, this is where the community recognizes the idea of a quantum, somewhat mature idea of a quantum computer was introduced, and this is Richard Feynman, the famous physicist, at a meeting in 1981. And this was brought up, Feynman was an expert not just in physics, but also in computation. Having worked on early computers back in the Manhattan Project, and he was motivated at the problem of simulating quantum systems and the fact that that's very hard to do on classical machines, Turing machines, or the actual practical machines we use nowadays, which led to that idea of quantum computing. Importantly, you hear a lot of introductions of quantum computing talking about how Moore's law and things are shrinking and we're going to come up against a quantum frontier. I don't think that's what led. Feynman was also an expert in nanotechnology. It turns out in the 50s he gave a lecture on that kind of stuff. But really the motivator for quantum computers was about simulating quantum systems and how difficult that is on conventional hardware. Now things start happening a bit more quickly. 1984, Charles Bennett and Gilles Brassard demonstrated, again from Wiesner's idea, which Charlie Bennett knew well, they demonstrated quantum key distribution, and this is kind of, if you like, the birth of quantum cryptography, which is another term you'll hear in this field. And then a few years later, David Deutsch took Feynman's ideas and made them a bit more precise, concrete, and introduced the idea of a quantum Turing machine for our computer science audience. I hope certainly theoretical computer science, putting it on a firmer foundation. Then I'll mention again Bennett, Brassard, and others, this quantum teleportation experiment you might have heard of in the mid to early 90s. And this is what I'm kind of earmarking as the beginning of the idea of quantum communications, yet another phrase that you'll hear nowadays. And then really things happened in the year or two after that. So Peter Shor in 1994 discovered this discrete logarithm application based on the others in this list and others' work in early quantum algorithms. And of course, you showed how we would use such a, at that point, imaginary machine to find the integer prime factors of large numbers. And that's where the field takes off. A very important other milestone here is just a year or two later, the idea of quantum error correction had kind of been not just identified, but really pinned down. And the acknowledgement that this imaginary machine is going to remain imaginary if we don't have quantum error correction. And already within a year or two of Shor's results, this research was taking off. So that just takes us up to the mid-90s, and that's really where things take off. I'll mention that Wikipedia now has a much more in-depth timeline that you can go into. Like I say, the field really takes off after this. I'll just mention that the anniversary of this Physics of Computation meeting that Feynman spoke at was just a few months ago, and you can go online at IBM's site and YouTube to see a special around that if you have the time. So I mentioned quantum sensing and communications and computing, and these are now kind of the recognized pillars, if you like, of quantum technology, broadly defined. And just to give us a frame of reference around these terms, if you'll grant me at the moment some qubit or whatever it is, our coherent quantum device, we'll get into this a little bit more soon. I've stolen a picture of a superconducting LC circuit from Science magazine. So if you'll just grant me one of these devices, which, like I say, people are chasing after, and we'll talk about in a second, then in the very, very simplest terms, a quantum sensor is basically one of these things with a bunch of stuff around it, some sort of interface and whatnot. But just to orient ourselves, a quantum sensor is kind of one coherent quantum device. And then if you think about two of these things and you hook them up somehow and get them to talk to each other, then you're kind of in the quantum communications realm, if you like. And finally, as you can probably imagine, into the quantum computing realm, you need, now we have dozens, we need hundreds, really we need millions of these things talking to each other in order to build an error-corrected quantum computer, which is where the field is trying to go. So just trying to orient us around these three kind of pillars of quantum technology that you hear about these days. And also, maybe this picture, this very, very rough cartoon might help you appreciate quotes like this one, which I really, really like. You know, why are we working so hard on these things? Well, even every bad quantum computer is a good sensor. And maybe this helps motivate that idea. So I said things have taken off. Here's some numbers from just last year, roughly drawn from a few sources. This is public investment in quantum technology around the world. You can see things have really taken off, especially in the last 2 years. On the order of billions of dollars going in. These are into public research programs or announced government incentives or programs, largely with the research community, the academic community. But it's not just public. Here's some famous slides that Michael and others at UTS created back just 4 or 5 years ago. The space of private quantum technology work was largely dominated here by big corporations working on hardware down in the bottom right, with a few startups on the left there. And just as of a year or two ago, the diagram looks something like this, with dozens of quantum startups now working in the software stack around quantum and whatnot. So really in the last few years, the amount of private investment has skyrocketed and is only doing more so.
Peter,
sorry?
There's now 3 people who are saying they can only see the first slide. I've seen them advancing quite naturally, but I've had 3 people say they can only see the first slide. Matthias, you're saying you can see all of them.
Shall I try? Oh.
So
Peter, do you want to unshare and then just try sharing again?
Sure.
Yeah.
Maybe I'll try sharing. I could try sharing a window and then making it.
Yeah, so we've got a mixed, seems to split down the middle, those who are seeing them advance, including myself, and those who are not.
Okay. So if I try sharing a window instead, maybe?
Okay, you can see that? Yep.
Can people see that?
Yeah, you can just
okay.
put it in presentation mode.
I'll put it into presentation mode. And let me go back a little bit. Any feedback, Ian, on how the audience...
They can now see them. Mark, how about yourself?
Yes.
Is that all right? Okay. So all I've done, for those who missed the slides, I did the history of the very, very brief history of the field and a quick introduction into sensing, communications, and computation, and just talking about some of the investment over the last few years and the way the field has really, really ramped up, which is why I guess we're here. Now I just want to get it. I want to get into the quantumness here very, very briefly, and then I'm going to go through an example in some detail. I don't know if it's the right thing to do. It's the first time I've tried it, and we'll see how it goes. But I mean, this is exciting time. The excitement is partly due to this idea. Some people use these words quantum 1.0 and quantum 2.0. So quantum mechanics, which has been around for 100 years as a theory, it's kind of transitioning from explaining things like the stuff we learn in chemistry class and physics class, the stability of atoms and conductivity in metals, and even stuff I heard about as a student, trying to explain the efficiency of photosynthesis even. And these kinds of explaining why the classical world is the way that we see it. By the way, when we say classical, we just mean non-quantum in this context. And it's transitioning into this exploitation. We're trying to harness these effects. And again, this is where the way we harness it is in the sensors or communications or computation. And words that are used around this are kind of coherent quantum effects versus incoherent quantum effects. So as an example of this, explaining things versus exploiting things. So to understand classical computing, we need to understand quantum mechanics, because electricity is not just currents and voltages or even a bunch of classical point charges bouncing around, giving us zeros and ones. When you dig in and try to actually build an industry around this, the quantum theory of solids gives band gaps, and that leads to semiconductors. There's obviously huge improvements in that field of technology. But again, it's still incoherent in the sense that we're using these semiconductors still to do classical things. These transistors, they control the flow of many electrons, and really all we care about is whether these things are on or off, a kind of bulk behavior, a classical behavior. Now, so the quantum mechanics has improved the way we do this classical information, but we aren't, so we're harnessing it in some sense, but we're not harnessing it to do the next step, which would be kind of quantum information. I've taken this terrible photo of, I might be able to do this on an oscilloscope in my basement. So coherence is the next step. The control of single particles, electrons or photons or ions or Cooper pairs in a superconductor is kind of the idea to have. We want to dig all the way down and see if we can really control these quantum systems and harness their quantum effects. So a quick slide here on the various kinds of coherent quantum systems that the world is kind of racing to harness. And this slide is courtesy of Mick and the team at UTS again. I'll just briefly go through it and we can get into more detail on this later on. But roughly kind of split into generations. Early attempts at this, ion trapping was an area where these quantum effects, these coherent quantum effects were demonstratable, often for the first time. But roughly speaking, these things are fairly slow. They're fairly large on the millimeter to centimeter side. They require, for example, vacuum systems and laser cooling systems. You know, if you see one of these ion trapping, certainly early ion trapping experiments, they fill a room. And I'll just say that there's a few companies that this technology is still being pursued, and there's a few names of companies there working in that area. You can think of second generation moving on. Things are getting faster. They're getting smaller. There's other physical systems that we're trying to control to do this kind of stuff. Vacancies in diamond structures, superconductors, which we hear about a lot, certainly recently. Discrete or discrete variable optics. And these things are faster, smaller. They still require cooling, and sometimes down to millikelvin levels, so that's quite difficult to do. So they have their drawbacks as well. And there's several companies, logos we can pop up, working around that technology, also still being pursued. And then things moving on, again, advances in diamond dots, silicon dots, what we call continuous variable optics, superconductors, kind of improvements and advancements in these technologies that are making them faster, making them smaller. Some recent results out of Sydney showing, out of University of New South Wales in Sydney, showing that you might be able to do this at higher temperatures, which would be good, be less restrictive. And again, oops. A bunch of logos of companies working in that area, and then really looking to the future where there's a bunch of question marks. There's very exotic types of systems that we might imagine using, a large class of them called topological qubits. Still, their existence is still, to some sense, debated, but the theory is very, very enticing around these kinds of systems for error correction purposes and things like that. And for example, Microsoft is working in this space. So there's a race on for all these different technologies. There's just a quick overview of them. I want to step back and dig in to one technology and get across some quantumness for you going forward. And then when Michael speaks in the second half of this, he'll say maybe a little bit more about some of this stuff. So quantum schmonum, and I hope this isn't a mistake. I'm going to try to dig in here. So famously, there's no simple way to explain or understand quantum mechanics, despite the exponentiating number of popular articles that you can read nowadays, where you hear things like exponential state space and things like that. You really can't put your finger on one thing that makes quantum special. You hear all these different kinds of words. The field theory is probabilistic, there's uncertainty, there's superposition, there's interference, there's entanglement, non-locality, and if you really get into it, you'll see a word called contextuality. And frankly, the field of experts there's still debate and discussion and research around how exactly quantum technologies derives their power. It's subtler than one kind of way to understand what it is that quantum technology, how it is gains an advantage over classical technologies. Like I say, I'm going to dig in. I'm going to pick one of these areas, and it's a good one, I think. I'm going to look at interference. And here's a screen grab from a lecture from Richard Feynman, who in his lectures on physics from many decades ago identified this as an area where basically all of the peculiarities of quantum mechanics can in some sense be derived from this interference effect. Again, up for debate. I've just said that you can't point at one thing, and when you go through quantum algorithms and whatnot, it's not clear. Sometimes it's entanglement, sometimes it's interference. But anyway, we're going to dig into this one and try to get the audience here to appreciate a little bit of this. So quantum interference, and I'm going to start with consider a fair coin. Here's my little blue coin cartoon. And by fair, of course, I mean that the probability of heads is 1/2 and the probability of tails is 1/2. And so nothing hopefully strange going on there. And then as a physicist, I'm going to come up with a very expensive coin. I'm going to build an optical setup in my laboratory. And this coin is going to be a photon. And I've taken this diagram for a specific reason. This is a famous paper that I'll mention when we're done. And the way I'm going to create my very expensive coin is I'm going to fire a photon down this interferometer, and it's going to bounce off a mirror and say, hit what we call a 50-50 beam splitter. And that means it has a 50% chance of being reflected, as that just showed, or a 50% chance of transmitting through the beam splitter. And then I've got these detectors at the end that go click, and I can count the clicks just like I can flip coins, and I will see exactly the same probability distribution. If I call, say, the upper detector heads and the lower detector tails, I see 50-50 probability. Okay, so just a very expensive coin that I've built. And now I'm going to consider two coins, and just for ease of differentiating them, I'm going to color one of them blue and one of them red. And hopefully everyone will agree that if I flip these two coins, that the sample space now has 4 outcomes in it. And you'll see these 4 outcomes: heads, 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 tails, tails, heads, and tails, tails, with 1/4 of the time. And lo and behold, I put this into my physics experiment, and I see exactly this behavior going on. So I can put a blue photon and a red photon through the interferometer. And for example, the blue one reflects and the red one transmits, and I get that outcome, and I will see that I get that outcome 1/4 of the time. And I won't bother to animate it, but please trust me, if you do this experiment, you'll see the other outcomes with exactly the same distribution. Okay, so now what I'm going to do, I'm just going to redefine my sample space. I'm just going to reorganize the data and say I don't care whether it was heads or head tails or tails heads. I don't care what order the two coins are in. I'm just going to call that one outcome. They're independent, so my rules of probability tell me I add those probabilities, and of course I get 1/2. And nothing's changed. All I've done is just redefine my problem. So I would see it in the lab. And if I think about it, though, what I've really equivalently done is I could just say, OK, let the coins be the same color, because I don't care about the order of the coins anymore. So I could just make them the same color. And that is exactly what I would see with 2 blue coins, for example, that distribution down on the bottom left. And now I can go to my lab and I can do this experiment with 2 blue photons in my lab. And off I go, and I see, for example, that outcome happen where both the photons come out of the top. I see in another run of the experiment, I might see them both come out of the bottom. And the thing is, I never see anything else. So the distribution of this experiment of 2 blue photons, the heads and tails outcome never happens, again, up to experimental accuracy. And that is a stark difference between the classical distribution and the quantum distribution. We have now seen a purely quantum effect, it's a famous example of the Hongo-Mandel experiment from 1987, and that's where I've taken that diagram from. So this kind of captures, this is a purely quantum effect, that interference, the canceling of those 2. If we think about the classical probabilities, the heads-tails outcome and the tails-heads outcome, that just can't happen in classical physics. And this is the kind of coherent quantum effect that we're trying to harness going forward. So I thought I'd pause there in case there are any questions, Ian, as I know that was probably new to a lot of people. I don't know if it's a good idea or not.
Let me take the advantage of asking a question. So I was with you until you went blue.
Okay.
What changed?
Why? Yeah. So I mean, that needs to be done. That is if you like, that's how I get the coherence into this problem. So as I was trying to get across, if one of the photons is blue and one of the photons is red, they're just like 2 coins. They are 2 independent probabilistic systems, and the probability outcome looks exactly like if I was just flipping 2 coins. It's really important that the 2 particles, in this case photons, have no other the way you see these quantum effects, like interference, which is the one we're just demonstrating, the kind of, it's a very grandiose way to say it, but if in principle the universe has any way to identify which particle was which, you won't see these effects. And that's exactly what this Hongo-Mandel experiment says. But if I erase that distinguishing information somehow, if I make this system coherent by making the 2, I've used the example of color in this experiment. Actually, in the Hongo-Mandel experiment, they didn't use color, they used timing. But the bottom line is, if I cannot in principle tell the difference between 2 events, then basically what we've learned is that in quantum mechanics, both of them happen. And they can happen with different signs in a more complicated probability theory called, we use things called amplitudes in quantum mechanics, and they can cancel, and that's exactly what happens in this case.
Can I ask, I'm going to dare to ask a follow-up question. Is there a tolerance in that difference? So if there was, color means wavelength, for example, if there was a difference of a fraction of a cycle versus multiple cycles, or a fraction of a hertz versus multiple hertz.
Yes.
Tolerance.
Absolutely. So, and in fact, like I say, the original Hongo-Mandel experiment, they used the timing of the photon, so the arrival time, as their distinguishing degree of freedom, as we call it. And you can vary that continuously. And the data from their experiment is actually a dip where you see this thing go down continuously, this probability of what we call coincidence, the heads-tails outcome. You can see that probability continuously decrease as what we call the wave packets of these 2 particles overlap. Then they become perfectly overlapped and it goes to 0. In principle, it goes perfectly to 0. In real experiments, there's always noise. There's what they call dark counts and things like that. In the detectors, it always gets messy. But in principle, it would go perfectly to 0. And then as you make these particles distinguishable again, that coincidence probability would come back up. So there's a continuous transition, if you like, in this case.
Wow, thank you.
Cool. I guess I'm not sure how I'm doing for time, but maybe in the interest of time, I better move on. I think I've got one more slide to go through before passing on to Mick, but very happy to answer more questions later on in the session. But carrying on from that really the simplest non-trivial, well, photonics quantum interference experiment. You can imagine scaling this up, and you might have heard this phrase boson sampling. So imagine just taking lots of photons in a huge complicated optical network with lots of beam splitters and phase shifters and stuff in it. And that's what this gray box is supposed to indicate. Now I could imagine, okay, tell me what the probability distribution coming out of this device is. And it turns out if these particles are classical, if it's incoherent, if they're distinguishable particles, it's not too hard classically to compute what that distribution would look like. And that's the incoherent one from the very simple 2-photon example that we talked about a second ago. But it turns out computationally, and provably so, that to calculate the quantum distribution at the output is very hard. And in fact, this involves permanence of matrices, which is known to be sharp P hard for the complexity theorists out there amongst us. So this a really important result of 10 years ago was that, of course, this is in the ideal world, even sampling from these distributions, even approximately, modulo some conjectures that most of our complexity theorist friends accept, that this distribution is even hard to sample from. It's hard to create samples that you could convince someone came from one of these quantum distributions. So this is actually one route to this phrase quantum computational supremacy, and in fact was done in China just a few months ago. You might have heard about in the news a Chinese group doing quantum computational supremacy this way. And this is kind of exactly, this photonics route was exactly the way they did it. And I'll just finish up this section of the talk to say that going through all the physics of this and explaining it, I mean, it's really cool stuff. However, that distribution is not so useful. We don't know any applications of that boson interference pattern or distribution at the end there. So I think with that, if it's all right, I'm going to hand it over to Michael to take this forward, which means I should stop sharing my screen. Is that all right?
Yes, we can now see Michael. Thank you very much, Peter.
Great. Thanks, Peter, for that explanation. And hopefully you can all see my screen. Is that all good? Or great. So you can all see my main screen, just to get a verification from.
Yes, we've got a quote from John Preskel.
Preskel, great, awesome. Okay, thanks for that explanation, Peter. That was a great, quick overview, and I absolutely applaud your attempt to explain boson sampling in like 4 slides really, really well. I'm actually going to dive a little bit more into that idea about quantum computational supremacy, but also talk a little bit about quantum computing application development and the challenges around that, and what it is that's actually going on with a lot of this commercial activity in the space. So as Peter mentioned, just late last year, there was this great experiment out of USTC in China where they did this boson sampling demonstration, and that was built upon by some original theory by Scott Aronson and Alex Arkhipov out of MIT about 10 years ago. And so that paper came out around 2010-ish, around then. And around that same time, John Preskel, who's really a great theoretical physicist out of Caltech, and who now also works partly at AWS, who works on quantum computing and quantum field theory, coined this term quantum supremacy. And as he said, so basically what he was explaining was that, we would soon be coming into an era where quantum computing devices would get good enough that we'd begin to see the first demonstrations of quantum computations where there was really no possibility to emulate that computation on a classical computer at all, which was really quite an interesting step, because the reason why this is quite a fascinating idea is it would have been the first time that a computation was performed that was quite clearly, in some sense, a computation in the formal sense, but that was distinct from the traditional Turing machine model of computing, which we've been using since, the turn of the 20th century. Now, I'm going to dive in a little bit more on what I mean about those ideas. So what we're talking about here is, like, imagine you have some sort of application. What we're expecting here is a behavior where we see the classical cost in performing a computation radically explode, while the cost for doing this on a quantum computer stays, relatively tame. Okay, so generally the task in identifying a demonstration of quantum computational supremacy or quantum computational advantage is perform a quantum computation that cannot be performed classically for any reasonable cost in time, or potentially memory, inaccuracy, queries, communication energy, or really money, or really any way of good, quantifying the cost of your computation. For the computer scientists among you, at least the theorists among you, what I'm talking about is complexity theory. And what we're talking about here is really two different models of computation. And so the big issues which are really confronted in identifying applications with this sort of behavior is where the quantum computers can exponentially outperform classical computers. But more importantly, that, are quantum computers literally more powerful than classical computers? And that's, as the computer scientists among you would know, like, actually proving clear separations in models of computation or complexity classes is a very difficult thing to do. And this is a problem that the quantum computing community's had to sort of directly confront. So once you've just you could think about that meta question, are they more powerful or not? That's somewhat philosophical, but then you could focus in on actual applications and ask which computations, like which particular applications do we see a radical divergence in runtimes or cost in doing a computation? And then finally, there's a question which is a bit more based in physics. Quantum computers that we have now all have errors involved in them intrinsically. Controlling individual quantum systems at the levels required to do quantum computation is not as precise as we'd like, or not as precise as the theory would like. And this is what Peter alluded to actually when he was discussing this Hongu Mandel did. You never quite perfectly necessarily get to where you want to go to and where the theory says. But it turns out that you can if you do clever things around the way that you encode your qubits and the way you define your systems. But there's a cost in doing that, and it requires creating even more qubits and making even bigger computations. And so there's a whole question here about whether we can go beyond the classical frontier without fault tolerance. And as Peter has said, we've just received a demonstration of that by USDC, and I'm going to talk a little bit more about some other examples of that. But in all this discussion, I haven't actually talked at all about what that graph is actually signifying. So in any computation or for any application, you can think about the fact that all computers have basically a maximum cost that you're prepared to pay in doing a computation. That could be time, money, memory, whatever. Like in any given computation, there's sort of a notion of what can maximally be done with a classical computer. Likewise, the same is true on a quantum computer. This is especially the case for a quantum computer that isn't using error correction or is not a fault-tolerant quantum computer. In fact, with the sort of quantum computers that people are developing now, what you'll find is the longer the device runs, the more likely it is that your computation is not going to work. Similarly, the more qubits that you use, or the more amount of memory that you use, the more noise you incur in the computation. And so, eventually, if you need to use too many qubits to, encode your computation, you're going to find that it doesn't really work very well. So the sort of scenario we're really hoping for is typified by this graph. So you have the digital runtime of a computation classically, like the best case digital runtime for a particular computation classically exploding, and the runtime of your quantum algorithm for that same application not exploding. And somehow you want to have these two curves cross over underneath that little red dashed line for the maximum quantum runtime. And so what the field has spent a lot of time doing is working out when these sorts of scenarios can happen. And especially in the near term, this is very much the scenario that people are trying to examine, is whether you can, do your computation in a way that's more cost efficient and less expensive than on a classical computer before your quantum computer turns into a pumpkin because of the noise involved. Okay, so the sorts of questions that we think about is, for any given application that you come across, you have an end user client or a domain expert say, can you find me a quantum algorithm for problem X? We need to determine what are the actual classical limitations of performing that computation. So how good can you run a classical computer for that problem? Is there a good theory for understanding how hard it is to do that application and quantify the resources required to do it? where are the actual bottlenecks in that computation? Then, you do that, and then you want to think about how you would approach this quantumly, and then you want to reduce the quantum resources, because at the moment, quantum computers are expensive and hard to build. You want to understand and minimize the errors that happen in that system, and ultimately, you want to optimize the implementation of any given particular application. So, and of course, there's also a scenario where classical computers are continually getting better. So it might be that while, you might find some problems where you see a radical divergence, it could be that, next year, a slightly better supercomputer is going to be released, and then it turns out it's actually more efficient to do on the classical computer than on the quantum computer. And that's always the thing you need to sort of understand when and how that's going to happen. Okay, so really broadly, there are 3 questions that you want to ask about quantum algorithms. What are the projected applications? When can we expect to implement it on a quantum computer? And how confident are we about the potential advantage a quantum computer can actually give you? So this brings me to the first example, which is basically a rehashing of the example that Peter gave, but in a slightly different context. So I'm going to talk about random quantum circuit sampling. And this was actually used by Google in their first demonstration of quantum computational supremacy in 2019. So asking these 3 questions I asked before, what are the projected applications? Well, as Peter alluded to, there's not actually a lot of projected applications for this kind of problem. The problem with this particular example is that we're literally looking at using random circuits as a benchmark for the performance of the quantum processor that they build. It's a carefully constructed problem where we're able to prove very strong things about the complexity of the classical runtime of the computation. And that's the reason why this is being used. There is one application which is about certified randomness generation, but there's other ways of doing this as well. So as to whether this is a giant billion-dollar application, it's less of a billion-dollar application, but more an interesting side effect, as far as we can tell at the moment. When can we expect to implement it? Well, it's already been done, but there's a little bit of debate about that, which I'll mention at the end. And how confident are we about the potential advantage? We're very confident about it, actually. It's provably exponential, subject to some common conjectures in computer science, which are very widely accepted. Okay, so as I mentioned, the first demonstration of quantum computational supremacy was a huge turning point in our field, actually. It was the first time a computation had been performed that could not have been performed with any sort of reasonable cost on a classical computer. And it was demonstrated by the hardware team at Google, who did this using a superconducting processor. There was a lot of people involved in this experiment, and it took them years to actually put together the device to be able to perform this particular computation. Very, very, very roughly, to condense a lot of pages of material down to one little point, there was a radical difference in the runtime and energy cost in performing this computation. So when they did this experiment, they finalized this experiment in 2019, the best supercomputer on the planet at the time was the Summit supercomputer. And what they found is that for the random circuit sampling applications that they examined, it took about 200 seconds on Google's Quantum Sycamore processor, and they estimated it would have taken about 10,000 years to perform the same computation equivalently on the Summit supercomputer. In terms of energy, there was also a radical difference in the amount of energy required to do the computation. Let me talk a little bit about what I mean by quantum circuit sampling. So in all of this conversation so far, you'll notice that we haven't actually really mentioned what a quantum computer clearly is. So in Peter's part of the presentation earlier, he gave a hint of this. He explained the boson sampling problem, and that is a type of restricted model of quantum computing where you essentially build a computing device out of basic linear optical elements. Okay, more generally, you can always think of a quantum computer as being akin to a classical, logical computer or a classical computer, except with quantum mechanical elements. So in classical computing, we can always think of a computer as being driven by logical circuits. So you might recall from back in high school or at university, you would have talked about Boolean logic circuits with AND, OR gates, and the like in order to perform your computation, where you'll have bits coming in at one end, where you'll have an input, you perform a circuit, and then you get some output of bits at the other end. The same is true quantum mechanically. So I've got a picture here of what I'm going to call a quantum circuit. Possibly not helpfully, or possibly helpfully, I've drawn it in 3D, and then the direction going from left to right is actually the time. So that's quite common in common way of representing a circuit, and it's also 2D in the spatial directions. And the reason for that is because actually when you see a quantum circuit diagram, normally you wouldn't have done in 2D like that, but this is a nice presentation. I want to make it look pretty, but also because a lot of the devices which people build now are actually based on a 2D lattice. So you have a circuit where physically your qubits are laid out in a 2D lattice of some kind, and then you have quantum logical gates connecting the qubits in that lattice, and then you act these gates in time, as you would sort of somewhat akin to a classical computer. So, you see there, we've got single qubit gates, we've got 2 qubit gates, and on the left-hand side, you have an input encoding, and on the right-hand side, you'll have your output of your device. So, okay, I'm a computer scientist, and I like to break things down to simple tasks where you have well-defined problems and well-defined inputs and outputs, okay? So, very simply here, we could ask the question, the task here is prepare a measurement samples from a quantum circuit, or rather, emulate the output of a quantum circuit. Now, quantum circuits have probabilistic outputs. Peter alluded to this as well earlier. So that's a bit of a thing. And so on a quantum computer, how would you do this? Well, what you do is you prepare the circuit, you run it, and you examine the output, right? You do the measurement of the output, you'll get a series of samples of ones and zeros out according to a probability distribution, which is defined by the quantum circuit. On a classical computer, one way you might want to do this is to think about, well, classical computers can be probabilistic, but that's, a whole other theory. But on a classical computer, one way it might be to say, okay, what we're going to do is try to compute the histogram of potential outputs of that quantum computer. So all of the probabilities are well defined, and there is a methodology for calculating the probabilities from coming out of a quantum computer, or the probability is describing a quantum computation. So we might want to try to just compute the histogram of all the potential outputs, and then use that to prepare an algorithm of some kind to prepare the samples, just to completely emulate the output of that computation. And you could ask the question, is this the best way? And the answer is, well, it's complicated. Sometimes it might be the best way. For certain families of circuits, it's not the best way at all. There are other ways of simulating the outputs. As I mentioned, classical computers are probabilistic. Sometimes it's very natural for certain quantum computations to be simulated very simply by a probabilistic classical computer. For other families of quantum computations, it might be that there's particular symmetries that makes this problem very easy on a classical computer. But in general, we don't think this is the case. And let me give you a great example why, and I'll talk about a couple more as we go on. So let's talk about the random quantum circuit sampling proposal. So this was research that we did at UTS in collaboration with Google and NASA in developing the theoretical background to this quantum circuit sampling problem. So here, essentially what we're going to do, instead of considering sort of the general case of an arbitrary circuit, we're going to think about a specific family of randomly generated gates. Very, very roughly, you start off with about on the order of around 50 qubits, then you have random single qubit gates and a certain family of 2 qubit gates are applied. And you're going to have more than 20 layers of 1 and 2 qubit gates in this computation. So the computational task for a classical computer to perform is prepare measurement samples from a random low depth quantum circuit. So 20 layers of gates is actually not very many. A classical computation does millions without there being an issue. But in a near-term quantum device, because of noise, we have to limit the depth of these devices a lot. All right, so as I alluded to before, how might we do this? On a classical computer, as I said, you can compute the histogram potential outputs and use it to prepare samples. Before, when I said for a generic circuit, is this a good way or not to do this? And I said it depends. Turns out for these random quantum circuit sampling examples, or this family of problems, this is actually more or less the best way of doing this on a classical computer. And you can prove very strong theoretical statements around that. So assuming theoretical computer science makes sense, as best we understand it, that the families of complexity classes that we have in classical computing behave as we expect that they should. And the random circuit outputs are as complicated as the non-random ones, which is a somewhat strong assumption, but it's a very common assumption in theoretical computer science. Then it is the case that the best way of simulating this on a classical computer is to basically compute the histogram. And you can also prove that computing the histogram of these devices is actually extremely hard. And you put very tight run times on that. So we end up with an example of a problem that looks like this. What we see is like a radically diverging runtime. It actually takes exponential cost to compute the histogram of these circuits. The quantum case, we just run the circuit, right? And what Google demonstrated in the lab was that they were able to actually perform this computation in such a way that they were able to get under that red dotted line. So we're actually able to see this before in an example where it would take a huge amount of resources on a classical computer to perform the computation, and a reasonable amount of resources for a quantum computer to perform this calculation. Now, so their theoretical proposal for this original random circuit sampling experiment was proposed in 2018. It was published in 2018. In 2019, we saw the experiment. Actually, and interestingly, in 2019, IBM argues that if you were to take the Summit supercomputer and reprogram it to work in a way which it doesn't normally work, you might actually be able to perform this computation in 2.5 days instead of 10,000 years, which is a very interesting paper. In early 2020, what we saw was Alibaba, the research team at Alibaba claimed it takes less than 20 days to perform a classical simulation using an updated version of a set of algorithms for simulating, or for actually simulating the histogram of these circuits. And so the reason I'm explaining those points is because, as I said, these things are a moving target. While the exponential divergence is not really a moving target, it's quite clear with this problem that it seems to require, the best case scenario you can have with a classical algorithm is an exponential runtime if the theory holds up. However, we're seeing subtle improvements to the algorithms for computing this still, and that actually makes some changes in the margins. So yeah, this is an active area of study and a very interesting area of study for people to pursue. Okay, so that was quantum computational supremacy. I wanted to give you a sense of how these scalings work for different sorts of problems. And that in some sense is, a story which to some extent is evolved. And now, we're very clearly into this era of quantum computational supremacy, where we now can build devices which are capable in some instances of outperforming classical computers. So where we are now is essentially on the far left-hand side of this story. So the device that Google built and the USDC device, they're roughly in the region of 50 to 100 qubits in terms of the number of qubits required to perform these computations, or in terms of the processors they're capable of actually manufacturing and building, getting to work reliably. Okay, but in order to have broad quantum advantage for a wide range of useful applications, we actually require millions of qubits. And the question is, how far away from that goal are we as a field? Well, IBM last year published their roadmap for their internal development of their quantum processors. And IBM are anticipating that by 2023, they're going to be able to build quantum processors that are reliable and of reasonable quality on the order of around 1,000 qubits by 2023. Google's roadmap, which was published earlier in 2021, they estimated that by 2030, they'll be able to build quantum processors in the regime of around 1 million qubits. So as you can see, the timeline here from getting from where we are now, which is we've literally just fired the starters gun on building devices which are better than classical computers, to being able to have devices which actually might be able to deliver some quite significant advantage to commercial applications. We're sort of looking on a 7 to 10 year time frame for that sort of device to be created. So right now, the entire field is essentially, focusing on two things. Firstly, building these devices, and secondly, trying to work out what the application space looks like, and what are going to be the first commercially useful and viable applications. So there's a wide amount of research going on right now in the field. Huge amount of commercial interest is coming in, where end user domain expert companies are looking to work out how they can best exploit quantum computers in order to, deliver some sort of commercial product. And they're working, so you have end user domain experts working very, very closely with experts in quantum computing and quantum algorithms in order to identify what are the best targets and and trying to develop things like IP portfolios in order to understand how, in order to take advantage of quantum computers when they come online. It might be helpful would it be helpful if I stop for questions here at this point before I proceed?
Michael, it's entirely up to you. If you've got more to run through, but
okay.
There are questions percolating along.
Okay, great. Okay, I'll keep moving then. All right, so there's a lot of commercial activity. Let me so as I mentioned earlier, one of the bigger issues right now is that while people can identify, a broad range of potential applications of quantum computers, they require a lot of qubits to perform them. So, there's on the right-hand side there, you'll see there are many very interesting potential applications that people are exploring. For example, catalysis nitrogen fixation. They're looking at like the properties of simulated properties of chemical systems to produce better batteries, semiconductors, biotech and drug design, all sorts of things like this. And what the community is very much working on developing more efficient algorithms, pushing down the requirements for these applications in terms of quantum computers. Like, how can we demonstrate these sorts of, or use smaller quantum computers, which require less resources, to actually demonstrate these sorts of applications? So that's a very, very big focus of the community right now. So let me take a bit of a step through some of these different applications and the broad sort of sets and families of applications according to the criteria I discussed earlier. So the first application, which is absolutely worth mentioning, is Shor's algorithm for factoring. As Peter mentioned earlier, Shor's algorithm was discovered in 1994 by Peter Shor, and what he found was an efficient quantum algorithm for finding the prime factors of large integers. That sounds very mathematical, but it's actually an extremely important problem, because the difficulty of that problem classically underlies most of the cryptographic systems we use on the internet today. So the protected application in this space is breaking cryptography. For example, the RSA crypto system and the elliptic curve crypto systems are broken via Shor's algorithm or variations on Shor's algorithm. When can we expect to implement it? Well, the best theoretical work that we've seen is, it started out actually at gigantic numbers of qubits, and as of last year, it's now at about 20 million qubits. Now, thinking back a couple of slides, I pointed out that Google is anticipating being able to build processors on the order of 1 million qubits within the next 10 years. So the gap there is now only an order of magnitude between what is going to be possible to physically build versus what is theoretically, the worst case scenario for breaking, say, RSA 2048. And that's around 20 million qubits. So the gap is actually not that far away, and that's actually creating a huge amount of research into developing cryptographic systems which are not vulnerable to Shor's attack, or not vulnerable to quantum attacks with quantum computers. How confident are we about the potential advantage? I mean, extraordinarily so. We built the internet security based on the presumed classical difficulty of this problem. So as I mentioned, there's now a huge amount of work worldwide in trying to understand the capabilities of quantum computers to attack crypto systems. Mostly that focuses on trying to develop crypto systems which are not vulnerable to quantum attacks. And there's been a very large program run out of the National Institute of Standards and Technology in the USA, coordinating worldwide researchers to develop basically replacements for the crypto systems which are vulnerable to attack by Shor's algorithm. And that's, one of the most interesting application spaces at the moment, and possibly the most important, because it has, if we don't develop crypto systems fast enough, we're going to have a very large problem with internet security that goes beyond the problems we have now already. The next application space I really wanted to mention was quantum simulations. Again, this sounds extremely academic. So why you want to build a quantum computer? Because I want to build a thing that simulates quantum circuits and/or other quantum computers. That feels very tautological, but it's actually a huge area of potential applications of extremely high commercial value. So what are the projected applications? Well, the biggie is quantum chemistry. And what that actually involves is the discovery of new materials, new methods for energy transport and storage. For example, building more efficient batteries, which is obviously a huge problem now for transport and just energy production in general, and drug discovery. When can we expect to implement it? Well, the best predictions right now is we'll be able to have demonstrations of quantum advantage. That is, we'll be able to develop commercially useful applications of these quantum simulation algorithms probably within a decade. And we're very confident here about the potential advantage delivered by quantum simulation algorithms. It's another example where you can say very strong provable statements subject to conjectures of computer science. And the flip side of that, though, is a lot of these things are application development dependent. So depending on the application you actually care about, the level of advantage might vary. So as I said, it's not just us academics that care about this problem. Google's CEO made clear that their interest in quantum computing largely comes about because of this quantum simulation problem. They very much see it as being the best opportunity for providing high accuracy simulations of physical systems. And that is a very large commercial value for, Google and other many other big commercial companies. So just to give you a bit of a snapshot of where the research is happening in this space and what sort of things people are looking at. It's been extensively studied worldwide, as Peter said earlier. Feynman's whole notion, introduced the notion of quantum computing because he was interested in this quantum simulation problem, because it's been a long-studied problem in science. There is a very large back catalogue of results in quantum simulation algorithms, but I really wanted to highlight there's been a fantastic collaboration over the last few years between Macquarie University and Google, which has provided some of the best research in the space over the last few years. Also worth mentioning is the work coming out of Microsoft, IBM, and a couple of startups, Spacecraft and Zapata. In the near term, what we're very interested in, what most researchers are doing in this space is to working with end user domain experts on things like simulations of functional groups of molecules, active sites and catalysts, and the development of quantum materials, or the study of quantum materials to understand various effects in complex advanced materials people are developing. In the long term, it turns out that quantum simulation algorithms are actually key to a separation between quantum classical computers for solving linear and differential equation solvers. And as those of you who've worked in software development, you'll know that that is like a huge amount of the, differential equation solving and linear equation solving is like the backbone of many subroutines in software development. And better quantum simulation algorithms involve a better separation between quantum and classical computers for solving linear equations, and that's a big area of research as well. That's essential also for quantum machine learning, and finally for analyzing chemical structures. That's actually the big end goal as well, where people want to be able to use quantum computers to predict very strong things about chemical structures. It's also worth highlighting that many of the experts in Sydney have worked on quantum simulation. I just wanted to put a few names up there. It's actually a very broad area of research, and some of the best people in the world are actually based here in Sydney, working on these problems. Okay, talking about broad, I'm going to talk about broad utility algorithms. So the examples I've given so far are quite specific. They're great examples of exponential separations between quantum and classical computers. They're all kind of classic examples of this. But quantum computers are also going to deliver speedups which aren't so huge. Sometimes they'll be more like polynomial kind of speedups, which is more a way of saying that quantum computers can deliver an advantage, but it may not be delivered in such a dramatic fashion. It might just turn out that they become more useful than, say, the existing subroutine you have on a classical computer. Not dramatically so, but nonetheless, you'd prefer to use it because it might get you to an answer you would not have been able to otherwise. The best example of this, and generally what that means more broadly is that these sorts of applications and algorithms are probably not going to be particularly useful until you go to really large quantum computers and quantum computers get cheap enough to actually really deploy them. So in the community, there's been a huge amount of research in that space over the last 20 or 30 years, partly because it's interesting, partly also because you can say very strong things about the runtimes and the comparative costs between classical and quantum computers in that space. For example, there's a lot known about unstructured search, combinatorial optimization, various graph properties and networking. And when can we expect to implement these sorts of things? As I said, this is more like when we get to much bigger quantum computers. So 20 plus years is probably what we're thinking about there. It's definitely outside that 10-year timeline for these sorts of applications. And how confident are we about potential advantage? We're very, very confident about it, but it's not going to happen until we have really big quantum processors. So, and like I said, a very, very broad range of applications here that quantum computers begin to outperform classical computers in this space. The first example of this was actually a problem which people call Grover search. And quite simply, it's, find the only winner in an unstructured list. Classically, this requires you to query that list at least n times, because it could be that, when you're querying the list, you might just have really bad luck, and it isn't until the last thing that you check, you might find the answer. So you require typically around n queries. Quantumly, it was proven by Love Grover back in the mid-90s that it requires square root of n queries. So that's not a gigantic speedup, but it is a considerable speedup if what you're talking about is like the ultimate limitations of what you can actually compute. Another really good example of this is triangle finding, and that's a very understandable problem. It's Find a group of 3 mutual friends in a social network with n people. Classically, that requires n squared queries, whereas quantumly it's at most n to the 5/4 queries. So if you want to learn more about that, you can go to the Quantum Algorithm Zoo and have a look. A great example from Sydney, actually, on this sort of research is by Associate Professor Troy Lee at UTS, who's an expert in optimization algorithms and the sorts of algorithms that we're talking about here. And also the techniques for actually proving the performance of this kind of algorithms. So I strongly recommend go have a look at the Quantum Algorithm Zoo if you're interested and you want to dive into a bit more detail, or reach out to some experts and ask them about it. Okay, finally, in my wrap up of quantum algorithms, this whirlwind tour I've just given, I want to talk about variational algorithms, AI, and heuristics. And that's really where the bulk of commercial activity is actually happening right now. So what are the projected applications? Kind of everything, because you can actually fit into sort of variational algorithms, AI, and heuristics, most things. And so the goal here is to take broad sort of algorithms which are capable of being adapted to a broad range of problems for things like optimization, and trying to find good heuristic solutions for problems of interest. So in finance, a lot of end user domain experts are focusing on this. So Goldman Sachs, Deutsche Bank, Commonwealth Bank of Australia has even written papers on this. In aerospace, you have Boeing, Airbus, Lockheed Martin. All of the big aerospace companies have worked on this as well. Similarly, in chemistry and for things like batteries and things like that, we have General Motors, Volkswagen. I think I've written General Motors twice there. BP, Woodside, Merck. Industrial chemistry-focused companies that leverage these things at the moment have been exploring the space quite actively. Now, what's the downside? Well, when can we expect to implement it? Well, sort of now, but the timeline for actually seeing a real clear commercial advantage is unclear at the moment. How confident are we about the potential advantage? Well, this is where the issue is as well. There are some long-term advantages established for this kind of algorithms, but in the near term, it's very, very open. And that's why everyone's so actively exploring the space. They're trying to resolve exactly when they can develop applications or what sort of applications can be used for these near-term algorithms. Okay, really broadly, what I'm trying to explain here is that there's families of algorithms or families of very broad optimization routines and variational problems, and AI frameworks for developing algorithms, where you take a quantum computer and you leverage some sort of classical optimizer or subroutine, which is often very powerful, to help inform your quantum computer about what to do next. So you start with you run a quantum computation on one of these near-term devices people are building. You send the data to a classical computer, and it makes the decisions for you. So you do a whole lot of classical optimization to sort of work out the optimal landscape for some hard optimization problem. So there's been some excellent specialized software tools developed to try and help people get into quantum computing by exploring this sort of space, such as IBM's Qiskit, Google's Quantum TensorFlow, and Google's Cirq software packages. Now, but the challenges in this space is we cannot test these sorts of heuristic solutions on large problems because we don't have large quantum computers yet. So establishing sort of the long-term, monetary advantage in these sorts of applications is difficult. We have to work more we have to do more theoretical work to establish when there is and isn't an advantage. So some of the sort of questions that they confront is, how powerful does a classical optimizer need to be for a given problem? How costly is a quantum solution compared to the classical solution? And should the optimizer be quantum instead of classical? That sort of question is the sort of thing people are exploring quite actively right now. Okay, that's sort of my whirlwind tour, but there's a few things you should always keep in mind when you're thinking about quantum application development. And there's some things which are just straight up speed up kills, especially in the near term. Firstly, problems that are too big for quantum chips. Quantum computers right now, 50 to 100 qubits is as big as they get. So you're limited to encoding your problem on 50 to 100 bits in some ways, and that's an issue, right? So you won't be able to load in big data sets. So if you have to load and store lots of data, quantum computers right now are not going to deliver a clear advantage for you at all. Anything that involves lots of arithmetic, i.e. very long depth or long time running computations, aren't going to work because we don't have fault tolerant quantum devices yet. And finally, anything that's too inherently sequential is also going to be an issue for the same reason. Okay, so everything I've focused on right now was all around application development and algorithm development, and giving you an overview of the sorts of application spaces where people are hunting right now. I've got a very, very big snapshot of the entire field right now in terms of the international research landscape in quantum computing. So everything I've talked to you about was very much at the top end of that stack. It's about application development and algorithms. But quantum computers, just like classical computers, are actually a stack of technologies, all of which are very much in active development. So starting at the bottom there, we have hardware like qubits and quantum control systems are, physical devices that people are building, right, in a very specialized way. And then it moves through things like error correction compilers, which work out what is the best error correction scheme to be implementing given your algorithm and given the hardware that you're going to actually run it on. And you have things like logical quantum compilers. You want to do things like data structure analysis, people developing quantum programming environments, quantum programming languages, and of course, algorithm applications that I've discussed. Right now, like there's some of the big corporates in computing are all, the big tech companies are working across this entire stack of applications. So IBM, Google, Microsoft, AWS have teams that are working all the way from developing qubit hardware all the way through to the application space and on all aspects of those technology. But also some of the bigger startups are doing the same thing. So D-Wave, Rigetti, PsiQuantum, Xanadu, Honeywell's not a startup, but they're partnered with a startup to do some of this stuff, and IonQ. So those very large companies, very large efforts are now working across the entire stack of technologies required for quantum computing. The top end of the stack is more software, the bottom of the stack is more hardware, and there's a range of leading research institutes around the world. It's very much worth noting here that Sydney actually has some of the world leaders across all the different sort of aspects of the stack, which are available. Very much worth mentioning is the Silicon Quantum Computing Company at the University of New South Wales, which is a very big effort in developing quantum processes utilizing qubits constructed out of silicon circuits. Another company with highlighting is Q-Control, which is based out of the University of Sydney, which has had much of their main focus has been on the development of quantum control software. So, software which drives the quantum control system, which drive the qubits. I also want to highlight the research which has gone into quantum error correction and logical quantum circuit compiling, which is happening at UCID, UTS, and Macquarie. Similarly, like application development, quantum programming languages, the study of these environments, and the analysis of all of these things is actually a very, very big area of research at UTS and Macquarie. And with that, I think I might now hand over back to Pete, or ask any questions if anyone has any at this point.
There we go. Thanks, Michael. That's really quite fascinating. So, folks, what I'm going to ask you to do is put your questions in the chat, and I'm happy to call you out, and you can ask your questions directly. But I'm going to fire off with a couple. The first is around the stability of the qubits themselves, and as I understand it, there's a really, really short time horizon that you've got stability. You can actually carry out computation, but if you can compute fast enough, then you can get a lot done. Is that a correct understanding? Is there an issue with stability, and is fundamental limitation?
So yeah, quantum devices right now very much will have issues with stability. There's what we call something called a decoherence time. So when you try and isolate a quantum system, its natural qubits ideally are like these perfectly, completely isolated little particles of something, right? Which the rest of the universe can't even see. That's the ideal qubit, but that doesn't actually make for a good computer because you need to be able to talk to it, you need to act on it. And the more that you do that, the more likely it is that you're going to have imperfections creep in. And then naturally what's going to happen is the rest of the universe is going to try and force that qubit into being it's going to force imprecision in that qubit, which gets worse the more you actually try and do things with it. So there's a whole series of techniques for trying preventing that. So there's the theory of quantum error correction was developed in the mid-90s, and you can see that by basically putting more qubits together and using clever encodings, you can actually avoid this problem more or less indefinitely if you can build a big enough device. So it was an amazing observation that that's actually possible. But for the devices we have now, we can't, you don't begin to see that sort of perfect error correction occur until you get into thousands and millions of qubits. So the devices we have now, they're just not big enough to do that. So yeah, the processes and the computation we're performing now, you've got to try and squeeze as much as you can into the computation in order to actually, beat a classical computer or do something interesting. Actually, that random circuit sampling and boson sampling is exactly that. So the whole point of that was to find the most difficult classical problem, which could be squeezed into like the minimal sized quantum circuit. And that was the point of that whole area of research.
Right. And what sort of order of magnitude are we talking about with those coherence times?
Oh, well, it depends on the qubit dramatically. So some have insanely long lifetimes, but it depends on the qubit and how you're using it. So off the top of my head, for superconductors, I think we're talking sort of microseconds, whereas the gate times run nanoseconds.
Yeah, so insanely long is still measured in microseconds.
Oh, so that's not insanely long. No, superconductors, it's like, yeah, they're pretty quick. Silicon, how do I put it? Yeah, you can see some rare earth metals, some qubit-based rare earth metals, you can see coherence times, which can be minutes, but they're very hard to make gates out of. It's the flip side of that. So it's this big trade-off there actually in decoherence times versus the gate runtime. That's the thing which all these hardware companies think a lot about, actually. But then again, you look at some companies like PsiQuantum, and they have zero interest in, well, at least publicly stated interest is they don't care about the NISQ regime at all. They're just punching to build error-corrected devices from the beginning.
Okay.
Yeah.
Great. So, folks, I'm going to keep asking questions until I see some pop up in the chat. Another question is about error correcting codes. It's something very dear to my heart because that's what I'm like. There was a really interesting breakthrough when classical error correcting codes started to be more closely aligned to the channel that they were associated with. So we had short codes and we had turbo codes, which started to take into consideration extrinsic information, which allowed you to say, well, I'm not just going to try and apply my cookie cutter into this environment. I'm just actually going to understand the physical environment that I'm operating in, whether it's a radio channel, whatever the case may be. Huge improvement in terms of capacity, throughput, and error performance. When you talk about error correcting in the quantum environment, I'm assuming that the nature of quantum is being contemplated, and it's not just applying an LPCD code or.
Yeah. Oh, do you want me to take that, Peter, or do you want to take it? I'm happy to take that.
I would just start off to say that yes, I mean the quantum codes are becoming even more aware now. So first of all, there are analogs or analogies between the classical codes and the quantum codes, but the quantum codes are certainly quantum mechanical. Second of all, I think part of the improvement on quantum error correction, especially in the last few years, is by taking into account the noise, the nature of the noise that's decohering your quantum system. And some huge benefits can be gained in thresholds and things like that by saying, okay, actually, this is the kind of error that I expect far more frequently than another error. And I just wanted to pass it over to Mick after I say the Sydney has one of the largest quantum error correction theory groups on Earth. So I hope you're happy to hear that. Just to again plug some more Sydney.
Yeah, just actually, as Peter was, that whole line of research around what we call bias noise error correction. That's where you're really going to think about, like, do I have particular types of errors happening more frequently than other kinds of errors? There's the best work, one of the best papers in the last 2 years came out of the University of Sydney, actually. On that. It was a really excellent piece of work. But yeah, so more generally, yeah, absolutely. What he's saying, like, things have improved. I should point out, like, quantum error correction from the beginning, we sort of started with quite pessimistic noise models and then developed a theory that could handle those pessimistic noise models. And as we're learning more and building bigger processes where we have more understanding of the noise actually occurs in those processes. That story is changing a lot. The other thing which has really evolved in the last couple of years, and I think we're going to see huge gains because of it, is that the codes themselves and the way you use them is going to become more tailored to the architecture as the architectures get more advanced. So if I talk to my friends who are experts in quantum error correction, I'll say, what error correction code should they use? They will say to experimentalists, just build a 2D grid and use the surface code, which is it's a code optimized for 2D grids. Just use that. That's what they should build. That is the answer you get, which the experimentalists bang their head against the wall and say, what if my processor can't build a 2D grid? But the reality is what's going on now is we've seen a lot more tailoring of the codes to the processor. And that's huge. I think it's going to actually make a very big difference to these, pessimistic numbers, which is terrifying for Shor's algorithm, actually, because it could be that, the numbers come down considerably from that 20 million qubits. That scares me, actually.
Great.
Okay.
Awesome. So I'm going to put you on notice that I'm going to end tonight and ask you a question about blockchain, but we've got some real questions from the audience now. So one from Sky Kelly from Standards Australia. So Sky, can I invite you please to unmute and turn on your video and ask your question, please?
Sure, thanks, Ian. So look, my question is for Michael and Peter. What do you see being the greatest challenge for quantum computing in the next 5 years? And what role does standards play?
That's a great question, Sky.
I could start off. Yeah, that is, I mean, it's obviously the big question in some sense. What is the biggest challenge? I think, I mean, in the flavor of the way the question was asked with the standards dimension to it, I would say that maybe one of the biggest concerns is the kind of closing the academic openness that has led us to this place in quantum tech. The arena that Mick and I and others have been working in for 20 years. As industry and government to some extent get more and more involved, as the stakes get higher, there is risk to that academic openness being closed. So maybe I'll flag that one up, and that could, and there's an area where standards, or at least responsible innovation, can play a role, in the sense that we could set out policies around the sharing of the tech, over, making sure that no one player becomes dominant, these kinds of things. Some of the big players are using words like democratizing access to quantum hardware. So, I mean, they get it. But I think, just again, as the stakes get higher, I would flag that up as one of the risks. Mick, I'm not sure what you might choose.
Absolutely, what Peter said. But I would also like to say standards can also play a role in ensuring that there's actually a lot of work going on now into trying to develop good standards for the comparison of different quantum hardware. So, the field, of course, it's a science. So there's many metrics and benchmarks and all sorts of things developed, but not all of those standards are fantastic from explaining to a commercial end user how useful a particular processor might be, or what the likelihood is it's going to be able to be deployed for the problem that they care about, right? And so there's a lot of work going into finding good ways of doing that, and also good ways of developing tests that you might be able to perform, say, on your quantum computer in the cloud, to make sure it's actually really a quantum computer and it's actually doing things it's supposed to be doing, right? So this is not always an easy thing to do when you can't actually test all the outputs of the device because it's going to be too hard. So you've got to develop good, trustworthy certification protocols that you might want to use, especially when you've got sensitive data and sensitive computations going on that needs to be done. So yeah, I think there's a lot of work for standards, actually, like tons. And I think we're just now scratching the surface of that.
That's great, thank you. Ian, did you want to add anything to that?
I just want to say that standards, of course, is the most fun you can have standing up, and this is a really important area for us to be involved in from an Australian perspective.
Great, thank you.
Thanks, Sky, very much.
Ian, could I just say one more thing, because I think Sky sent a message around standards as well. Sky, Sydney Quantum Academy is involved with Standards Australia now. We've had a meeting, and one of my colleagues in engagement is kind of leading that aspect of things. So I'll follow up with you afterwards at some point, maybe next week or something.
Right, thanks, Peter.
All right.
Great, fantastic. And in particular, if we've got real capability here in the broader New South Wales area, as standards start to emerge in quantum, And given all the different layers they potentially can emerge, it's really important to develop a more unified national perspective and to be driving the standards as opposed to having them impact us. And that does, again, bring me back to the point of blockchain, which I will end my questioning. I'll ask you a blockchain question, but we've got a couple of others. We've got Helen. Helen's asked the question, have you looked at nanobots in medicine? And that potentially is a fairly broad question. Helen, would you like to unmute and ask your question, please?
So unmuting. Hi guys. There's a lot of programming, computing in having little nanobots go into broken joints and doing all the surgery. Have you thought about where that will fit, where the quantum programming will fit, the quantum computers will fit in that? Good question.
I'll let Mick answer the kind of application algorithm side of them.
Yeah, sure. I'd say we're not there yet in application development. So where that sort of thing would come in would be in, like, they already use AI and things like that in surgery, actually, like in precision surgery. And quantum AI, so quantum enhancement of AI is the way I should put it, is, as I said, there are some advantages which have been theoretically, demonstrated with math, but there are ways off, and understanding where quantum algorithms are going to be useful for things like AI is really just a work in progress right now. So as the devices get bigger and more complicated and capable of doing more things, so over the next really 3 to 5 years, I think we'll have a better ability to answer that kind of question. But yeah, I should also say that, I mean, if you want to get really small, there's certainly a lot of work into utilizing things like laser tweezers and things like that for doing like all sorts of things that are in the biological space. That's been an area of research. That's not really quantum computing per se. It's quantum technology in a sense. It's almost quantum. It's somewhere between quantum 1 and quantum 2, actually. Yeah. As a technology, that's a thing. People definitely work on that.
And that will be a demand area that is speed it up and simplify it and make it smaller and more and smarter. Yep. Okay. Thank you.
Thanks, Helen. And one of the points you raised earlier was around quantum chemistry, and I think that has enormous potential in terms of new discoveries, not just drugs, but also how systems and processes actually flow. So the absorption of penicillins and even just simple paracetamol, it's something which is largely a bit of a black box. So understanding how these commonly used drugs actually really genuinely work, I think would be really an interesting area for future study. Another question from distinguished Professor Fang Chen from the University of Technology. What are the potential applications in smart places? Now, Fang, if you'd like to unmute and ask the question, just a reminder that this is the 12th in our series of 10 Masterclass series leading up to the Smart Places Summit. And it seems quite appropriate that we've got this being the 12th in the series of 10 being quantum computing.
Thanks, Ian, and thanks, Peter and Mick. It is one of the best quantum computing tutorial I listened to, and thank you very much. And I was surprised that I haven't met up with Mick, but we'll extend that discussion later. The question here is, of course, related to the smart places. We heard all these fantastic stories, and they're just so keen to understand what the timeline look like. Like, when is, the time that we can look into some applications in reality? And then also, of course, we're all interested in smart places, and what kind of applications that in your mind you think may be taking off a bit earlier than others?
I could start off, Mick. I confess I'm not exactly sure what smart places means, or even the Internet of Things. I can kind of guess as just an old-fashioned physicist, I guess. But so I think one issue around the Internet of Things is certainly security, and quantum cryptography and key distribution and post-quantum cryptography. All of that conversation that we kind of, one of those 3 pillars that we touched on, sensing, communications, and computing. That communication side, clearly in a smart city, security and the upcoming conversation around quantum security has to definitely play a role at some point in that. Now, whether Your refrigerator is going to have a coherent quantum link to a quantum internet running key distribution protocols. I'm not sure. But I mean, I guess that is the kind of thing that is conceivable down the road.
So interesting, if I could just build on that. I mean, we've got, I mean, Fang is doing quite a lot of work at UTS on smart city, smart places, and it really is about understanding situational awareness, root cause analysis, predictive capability. And as we talk about future applications or future enabling technologies and existing or emergent areas, whilst, you know, sometimes it's a little fun just to throw some ideas around, what has always struck me is that if you dig a little deeper, and we just talked about a refrigerator participating in part of a you know, quantum key distribution. But if we talk about, for example, demand side energy management, where you've got large photons coming from an electrical grid now moving in multiple different directions, and those large photons might be redirected, or they might be tracked, or they might be reharnessed in some way, shape, or form. It strikes me that the convergence of what seems to be a fascinating but relatively limited area and existing physical systems, which we're starting to understand in different ways, might actually become a topic which is at least worth watching as these different technology areas start to converge. Our ways of thinking about energy flow, information flow, and the commodity flow through now multi-directional networks, I think would be very heavily impacted by the ability to think about those systems from a physics perspective and a chemistry perspective somewhat differently. So I just would put it out there that this is a space that I hope that we will see increasing convergence of emergent technological areas.
Yeah, absolutely. Just to jump in there too, and yes, that's a thing. So just to, Ian, as you were saying, yeah, I think there is actually a convergence beginning to happen increasingly. Quantum computing's gone through a transition in the last 2 or 3 years where prior to 2015 at least, or 2017 even, quantum algorithms research was largely the domain of mathematicians and theoretical computer scientists, working on things that will get you a publication in Fox and Stock, which are like, leading theoretical computer science journals. That was the goal, right? And it was like prove things as you can. End domain user experts, so people who are working on like the development of products or big industrial processes and things like this, weren't really involved in any of that. So it'd be quantum algorithms experts trying to guess what people might want and then trying to prove something about it, or more to the point, finding a point of difference in the mathematics of how the algorithms work and then building on that to try and do something. It's really a large fraction of what we do. And now the conversation is very much now between end user experts. So many companies are now, bringing in quantum teams, building their own teams, or working with consultants or universities to try and begin to take the first steps into that space. As Peter said earlier, actually, one of the big things is actually around network security. So often the first step for a lot of them is to look at the issues around how security vulnerabilities caused by quantum computers and what the timelines are like for that and what the solution space looks like. So there's been a large work in post-quantum crypto and general improvement of cybersecurity standards. And that's normally step one, because that's, as I said, like timescale is 10 to 15 years, but it could be sooner and we don't know. And that's scary when we don't even have the standards in place yet, right? So that's the thing where people start. And then they begin to look then into like how can you develop new products and things like this. So obviously in chemistry, that's direct. It's like really things which are clear, but more broadly around, a whole range of things people are beginning to explore. And I should say that the time is now in a sense. So because, we're 10 years, like how long does it take to develop a product on average? What is it, 7 years? If Google's going to have 1 million qubit device by the end of 2030, now is the time to really get going and start developing your IP portfolio and things like this for those potential applications. And so people are beginning to do that now. That's why that's happening.
So at the risk of just reinforcing the point about standards, because I really am a huge fan of standards. Our last session, our last masterclass was 6G, which is also targeted at the world of 2030. And as part of that exercise, we try to imagine the world of 2030. And if we really stood at 2030 and looked back at 2021, I think we would understand the world around us in a very, very different way. It's not just population and climate change. We would actually understand much more about nature and the way that the world actually operates. And I would expect that quantum would be much more commonly brought into conversations, or much more commonly part of our consideration. Going back to standards, the world of standards is trying to go through that same exercise of trying to imagine the world of 2030 through the lens of the United Nations Sustainable Development Goals, and saying we want the world to look like this by 2030. And if your interest was clean water, or your interest was security, or your interest was again manifold, looking from 2030 back to today, we would understand the world differently. So the way we'd be designing systems would be quite different. I'm getting ahead of myself. I'm going to throw to Tom, who's been very patient. Tom Zord. His question's about IoT, and one of the things, actually, Peter, you started with was a quantum sensor. And Tom's question is really about moving data. But again, our understanding of the world and our ability to sense the world differently will change the way we think about IoT. But Tom, without preempting, your question, please.
Oh yeah, my question is mainly around not so much the sensing, but the amount of data that we're going to collect, and it's going to be real-time data. Is quantum, and in my mind, I get excited about this, but is quantum computing this sort of solution that's going to be able to process lots of data in real time in order to get insight? And can it do that?
Thanks for that, Tom. I think Mick's probably in a better place to answer this than me. I'll just say around the quantum sensing, I think that's an accuracy improvement more than a data volume increase in some sense. So the idea of quantum sensors is to sense and do metrology in areas that you can do with accuracy that couldn't be done before. And examples are, for example, satellites with ion traps on them that could actually detect the difference in a gravitational field, whether someone was standing on the street or someone wasn't standing on the street, and things like that. But presumably that doesn't come with an increase in data. I appreciate that in an Internet of Things smart cities context, the data volume is a huge issue. And there's certainly, I still have confusion about which quantum algorithms need classical data to be input and quantum data to be input. And that's where I want to pass it to Mick, who could probably say more on that.
Yeah, throwing me the ball just as a defense is right in my face. No, yeah, what Peter said actually, so most of the quantum sensing stuff actually is about higher accuracy and not higher data throughput, mostly anyway. When it comes to quantum algorithms, some applications you could sort of, if you could have a big reliable quantum memory, you get a big advantage if you have a quantum computer. Building big reliable quantum memories is super hard though, right? And then you also have this whole problem of this is true for classical as well, right? We're storing huge amounts of data that we then use AI to pick through, right, to do things. And eventually, I'm guessing that's going to happen quantumly as well. When I say that to experimentalists, the people who build the hardware, they slap me. They generally slap me and walk out of the room because it feels so far off in the future, being able to build devices that are that big. Because you need it to be. Imagine a scenario where you could have a quantum RAM, where it could have considerably more memory than you put in the processor itself, right? So you have the ability to call RAM or call even a quantum hard drive as part of your subroutine. And we know, for example, things like linear equation solving and equation solving, that's definitely a thing. So if you can do that, you get a big advantage, but it's far off in the future in a lot of ways. So yeah, that's kind of where it is. I don't think it's been well thought through. At the moment, it feels like a far off future thing to me.
So things like routing traffic?
Oh yeah, routing traffic though is different though. It's things like that. I think where people are looking at is things like quantum algorithms for things like that are a thing people think about, but you sort of take the classical data as input and then look at it. So that, all sorts of quantum machine learning and optimization problems are things that people are examining now. And that often takes classical data as input as a starting point. I guess the only other thing I really wanted to highlight too is that there's a whole big area of research in quantum networking we really haven't touched on that much. And so people are genuinely interested in quantum networking in part because if you can build reliable quantum networks, you can actually interlink quantum computers around the world and get more computational power. And how best to leverage that is a thing that people are trying to examine. And what that means is a thing people are trying to examine. There's actually been some, there's a lot of things that just get interesting in that discussion, actually, about the different use of how you might leverage sensors and technologies and blah, and what happens when you interconnect them all. And that's just a thing people begin to think about now, I think.
Thanks.
Great. Thanks, Tom. We've got another question, and I am going to save question time for my blockchain question, but I've got a question from Mark Bailey. Good to see you, Mark. Specifically for Michael. So, Mark, if I could encourage you to unmute and ask your question.
Thank you for the enthusiasm and it's so
yeah, you can unmute my computer. Let me. Ian, it's nice to see you too. We were in touch when I was at the university a couple of years ago about quantum simulators.
Got a really bad line. Can I just encourage everyone else just to mute just in case?
Could be network here. Have you got me now?
This is coming through with a fairly substantial.
You maybe you figured it out. No, Ian.
What a pity. Okay, so Michael, now I'm channeling Mark Bailey here. For Michael, we were last in touch about quantum simulators in 2019. You were pretty skeptical at the time. Now this is Mark Bailey speaking, not me. What's your take on progress in this area since then, please? Question mark. I joined the call late, so please ignore this. I've already covered.
Right. So I'd have to go back and remember what the conversation was about. But what I'm skeptical about is not quantum simulation algorithms per se. They're very not a thing that should be too skeptical about. It depends on what you're trying to do is the question. So there's a thing that people call quantum simulators, which is something which is in some sense independent of quantum computing. So that's where you build a tailored simulation system specifically to simulate another quantum device. So instead of building a quantum computer, which is a computer, very much so, and then using it to simulate, you can still build a simulator which might simulate other systems. Now, I'm not skeptical about them working. They definitely work, but the question is to whether they're particularly, often what they do is mostly simulate systems which are very close to the original system in the first place. So understanding the full utility of those is actually a whole question, basically. In fact, there was actually a fantastic paper came out last week, I think, where a team at Harvard actually did a fantastic they built a very capable quantum simulator out of neutral atoms, which is a thing. So yeah, that area is progressing, but that's a distinct technology from, say, quantum computing, where instead of like looking at, I should say, like quantum simulators are very much analog simulators as opposed to being like a digital quantum computer. So yeah, the comparisons are all a bit different. That's what I would say. I hope that answers the question. And if it doesn't, ping me and I'll talk to you more about it later. Like, I'm not 100% sure what exactly the question was.
So Mark's saying thanks. Sorry for his bandwidth issues. He needs a few more of those photons traveling down his line in a reliable way. We've got a question coming in from Sky, but while Sky is typing, I'm going to ask just a broad question about the difference between programming for quantum computers and programming for classical computers, and where would you notice the difference?
I guess I can start, or Peter can, but like, I mean, it's totally different. That's one thing I should say. So, I mean, you actually will often fire up Python and start writing code in Python in the same way you do it with a classical computer. But the design of the algorithms is wholly different. At the moment, we don't really have quantum programming languages in the same sense as we do classically, actually. The closest thing we have is probably, and I'm going to get yelled at by my quantum programming friends, but Q# is probably the closest thing we have. That's been developed by Microsoft, and that's an attempt at developing a functional program, a precursor to a functional programming language, right? In that, you know, you can really call in, I guess I don't need to describe what a functional programming language really is, but most of the quantum programming environments that people have developed right now, you're literally, what you're code is doing is describing the circuit that's going to be run. And that's not a thing we do classically almost ever at this point, right? We have like layers of abstraction, which mean we don't have to think about that as much. Theorists will think about it when they're trying to do comparisons of algorithms. They will break it down to things like that, but normally the typical programmer or software engineer wouldn't be thinking about the circuit which the processor is actually implementing in order to run your, subroutine. Whereas at the moment, that's exactly what we're doing quantumly, because you have to work so closely with the devices that we have. So there's a very big difference. But in terms of actually the skills required, I mean, if you wanted to get started with some quantum programming, doing that's a thing anyone with any basic programming could do. Like, you can certainly go and get on a GitHub, download Circ, and start tomorrow, immediately, and then fire it up on, fire it up in your Python instance and go, right? And then that's a thing you can do, like right now.
So there was a very big move as we moved away from assembler type languages to compiled high level, almost natural language type or fourth generation languages, and those different layers of abstraction, as you mentioned. But there was a big change not so long ago when we started talking about distributed systems, and we talked about being able to run in cloud environments. And it required a different sort of thinking, and it required, even if you've got simultaneous processes running. Is that the sort of change we're talking about, even if we're not expecting to address the amount of memory, the circuitry? Are there differences that we must keep in mind that, you could actually, to Peter's earlier point, you could not get a result that you would expect because it's impossible? Is there some new dimension you need to contemplate in order to effectively program?
Yeah, I mean, so my friend Chris Ferry, who I always am arguing with about this, he will tell me that, the goal is that there should be no difference, right? That's, in the end, you shouldn't have to think about this. But I'd say right now you have to think about the difference between quantum and classical computing all the time when you're developing applications. So when I say the differences, I mean like literally the mathematics describing the thing that you're doing. You need to work with that and think about it. So it's very, very different from what you'd be thinking about classically normally when you're doing programming. It's pretty unusual when you're developing applications to be very worried about the mathematics describing the processor in the development of the applications. So barring a few very key subroutines in quantum computing, you need to think about that when you're doing application development. So, and that's why you'll find that the end user domain experts are working closely with quantum algorithms experts that actually have experience in the field to work on this sort of thing. Because it's not always going to be the case that actually it makes sense to do the thing you're trying to do. In fact, actually, there's a very big, interesting, so DARPA, the research agency in the US, has a very big call at the moment, which is, well, they just closed actually, which is all about identifying those key benchmark subroutines to provide targets around the performance of those, so that to make it easier for end user domain people and experts to actually, work on developing these sorts of targets and to help with programming eventually.
Okay, thank you for that very sensible answer. I think it'll be very, very interesting when we've reached the point with compute power and memory and so on that we effectively can, we can just rely on that compilation process to get us into the right ballpark. But if you spoke to someone who was possibly 20 years older than myself, they would talk about every single 8-bit of RAM or byte of RAM. Now, we're at the point where I'm going to ask you my question about blockchain, and in fact, I'm going to ask you about Bitcoin. So just had a quick search now. Bitcoin is estimated market value of $600 billion, and it relies pretty heavily on hashing, the SHA-256 hashing, in order to validate that the previous block is the right block connected to the previous block connected to the right block. And the ability to impact that is or the ability to either skip ahead or the ability to unravel is somewhat behind the basis of that distributed trust in at least Bitcoin and certainly lots of other distributed ledger technology. Does quantum computing represent a challenge for that, the ability to calculate the hash faster, to calculate the special numbers faster, to calculate the next block hash faster?
I'm just in the middle of cutting and pasting something into the chat, a paper about that. So yeah, so for the hash, Not really. I mean, yes, but not crazy. That's an example of something which is more like a square root speed up than an exponential speed up. Now, where there's in the signature, however, in Bitcoin, there's actually a problem which is around the fact that it uses something that can be compromised by quantum computers. So there is a quantum attack on various aspects of the signature scheme, and that's a problem for Bitcoin. It's not a problem for all of them, but it's a problem for Bitcoin. That's a thing. And there's actually, so I just posted a paper about that in the chat. Whether it's a near-term problem is unclear, because it has to be you've only got a limited window to make that attack, is my understanding. Like a really limited window. It's like seconds to make that attack. And quantum computers that fast, that capable, even though you might be able to break RSA maybe in 10 to, a reasonable instance of RSA in 10 to 20 years, being able to do it in seconds could be a whole other thing. So that's unclear. But for the hashing part of it, it'll be a while before I think quantum computers can really attack it. But anyway, have a look at the paper that's posted in the chat. They talk all about this, actually by Troy Lee, who's at UTS nowadays. He was in Singapore at the time. Actually, I'm not sure. He might have been at UTS just then. And Marco Toa-Michael, who was at UTS at the time, is now in Singapore, and a couple others, and Gavin Brennan, who's also at Macquarie University. I think they wrote the first paper about, extensive paper about this, actually. Have a look at it. It's really interesting.
I did notice the date on that paper was 2017. So
yeah.
The world has moved a little bit.
Yeah.
So folks, we seem to be out of questions for Peter and Michael. I have to say, I thought this was absolutely fascinating. We've lost a few folks who've jumped off the line, but who thanked you both very much, and let me add my thanks. I think, don't tell anyone else, I think it was the best session we had. We call them masterclasses. We know this one was a tutorial, but thank you very much for treating us gently. I think it was absolutely fascinating. And if we were there in person, you'd hear a thunderous round of applause right at the moment. So Peter and Michael, thank you very much.
Cheers.
That's the thing with lockdown.
Thanks very much, Ian and Mark and the audience. I just want to mention sydneyquantum.org for the Sydney Quantum Academy. We've got a newsletter and other things. Please come and check us out. We're a partnership with 4 of the amazing quantum groups here in Sydney. And as I think Mick and I have tried to get across, there's just an amazing amount of quantum talent in Sydney, and the Sydney Quantum Academy is reflecting that. And the involvement of people in this audience and the different classical computer science and all the other bits and pieces that go into it would be really great going forward.
And I want to put a plug for the conference, which is coming up in September.
Thank you. Yes.
Yeah. So the SQA is organizing a conference. It's Quantum Australia 2021, I think is the name officially. I go and check it out. Go to the SQA website, look at it, and yeah, look at the conference. We're going to have a great arrangement of speakers. Some of the world's leaders will be coming and talking, or coming, some of them virtually, some of them in person, and well, hopefully in person. Fingers crossed the lockdown's all over in time for us to be able to do that. But yeah, we'll have many leaders, including like the leaders of the teams of the Microsoft, Google, IBM, and AWS efforts. Actually, will all be presenting. Awesome.
Thank you very much. Gentlemen, thank you very much for joining this evening. And for the ACS audience, this session has been recorded. It'll be, we'll tell you about the recording soon. And as mentioned, we'll ask for a subset of the slides presented tonight. And this is the end of our series of 10 masterclasses, with number 12 tonight. So thank you very much, gentlemen, for being number 12 and proving that quantum is a little bit more unusual than most.
Cheers, everyone.
Thanks very much. Thanks for joining.